Picture this. A 6-year-old boy sits alone in his room, eyes closed, visualizing mechanical devices with such clarity that he can mentally rotate them, test their function, and improve their design without ever touching a single tool. This child possesses a mind so extraordinary that he will one day illuminate the world with alternating current wireless communication and inventions that seem pulled from the pages of science fiction. His name is Nikola Tesla, and his story begins not in the laboratories of New York or the workshops of Paris, but in a small village in the Austrian Empire during a violent thunderstorm that would prove prophetic. On July 10th, 1856, as lightning split the sky above the village of Smiljan in what is now Croatia, Milutin Tesla paced anxiously outside his home. His wife Georgina was in labour, and the midwife had just delivered troubling news. The child was being born during the peak of the storm, and according to local superstition, this meant the baby would be cursed with darkness and misfortune. But when the infant Nikola drew his first breath and let out a powerful cry, his mother looked down at her son and declared with quiet certainty that he would not be a child of darkness, but a child of light. How could she have known that this declaration would prove so remarkably prophetic? That this baby, born amid nature's most dramatic electrical display, would grow up to harness electricity itself and transform human civilization? The complete life of Nikola Tesla is a journey through genius and madness, triumph and tragedy, scientific breakthrough and bitter rivalry. It is the story of a man who could see the future with startling clarity, yet struggled to find his place in the present. What drives a human mind to such extraordinary heights? How does a boy from a remote mountain village become the architect of the modern electrical age? And why does the same brilliant intellect that revolutionizes technology also lead to isolation, obsession, and ultimately a lonely death in a New York hotel room? Over the next hour, I will take you through every phase of Tesla's remarkable existence, from his earliest childhood visions to his final tragic years. We will explore the inventions that changed the world, the partnerships that shaped industries, and the fierce battles that determine the very nature of electrical power as we know it today. But this is not just a story about scientific achievement. This is the story of what happens when pure genius collides with human ambition, corporate greed, and the limitations of mortal existence. Tesla's life reveals the price of being too far ahead of your time, too uncompromising in your vision, and too brilliant for a world not yet ready to understand what you offer. The Tesla family had deep roots in the mountainous region of Lika, where Milutin Tesla served as an Orthodox priest in the small village of Smiljan. This was not an easy life. The Austrian Empire's grip on the Slavic territories was firm but often brutal, and the Tesla family, like many Serbian families in the region, lived under constant political tension. Milutin was an educated man, fluent in several languages, and possessed of a sharp intellectual curiosity that he would pass on to his children. He wrote poetry, worked on mathematical problems for recreation, and maintained an extensive library despite the family's modest means. Georgina Tesla, Nikola's mother, came from a family with an extraordinary legacy of invention and ingenuity. Her father, Nikola Mandik, had been a skilled mechanic and inventor who created various household devices and small machines that made life easier for the rural community. Georgina inherited this mechanical aptitude, and despite being unable to read or write, she possessed an intuitive understanding of how things worked. She designed and built her own household appliances, created improved tools for textile work, and could repair almost anything that broke around the house. This combination of intellectual rigor from his father and intuitive mechanical genius from his mother would prove crucial in shaping young Nikola's extraordinary mind. But the Tesla household was also marked by tragedy. Nikola was the fourth of 5 children, and the family dynamics were complicated by the death of his older brother Dane in a riding accident when Nikola was just 7 years old. Dane had been the golden child, brilliant and charismatic, destined according to family expectations to carry on the family's intellectual traditions. His sudden death devastated the entire family, but perhaps none more so than young Nikola, who not only lost his beloved older brother, but also found himself thrust into the role of the family's great hope. The pressure was enormous, and it contributed to what would become a lifelong pattern of perfectionism, self-criticism, and an almost desperate need to prove himself worthy of the expectations placed upon him. From his earliest years, Nikola displayed abilities that bordered on the supernatural. He possessed what he would later describe as an unusually vivid imagination that allowed him to visualize objects with perfect clarity. He could construct elaborate mechanical devices entirely in his mind, test their operation mentally, and even identify flaws in the design without ever building a physical prototype. This ability, which he called his mental laboratory, would become one of his greatest assets as an inventor. But these same mental gifts came with disturbing side effects. Nikola experienced what would today be recognized as symptoms of obsessive-compulsive disorder and possibly autism spectrum characteristics. He was hypersensitive to physical sensations, unable to tolerate the touch of pearls, the sight of peach fuzz, or certain sounds and textures. He developed elaborate rituals and compulsions, counting his steps as he walked and requiring that all numbers in his daily life be divisible by 3. His parents watched with a mixture of pride and concern as their son displayed intellectual capabilities that far exceeded those of other children his age. At 5 years old, Nikola had constructed a small water wheel that operated smoothly without the paddle boards that were typically necessary for such devices. He caught frogs from a nearby stream and discovered that he could make them perform coordinated movements by gently stimulating them with small sticks, leading to his first experiments with what he called biological motors. The young Tesla's mind was constantly active, constantly questioning, constantly inventing. He would spend hours alone, visualizing mechanical contraptions and testing their operation in his imagination. His family often found him staring off into space, completely absorbed in his mental experiments, oblivious to the world around him. These episodes worried his parents, who wondered if their son might be developing some form of mental illness. School proved to be both a blessing and a challenge for Nikola. On one hand, his intellectual abilities were immediately apparent to his teachers, who marveled at his capacity for mathematics and his ability to solve complex problems in his head. He could perform intricate calculations mentally with a speed and accuracy that seemed impossible. When his mathematics teacher accused him of cheating because he solved problems too quickly, Nikola was able to demonstrate his methods and prove that his abilities were genuine. But school also exposed the social difficulties that would plague Tesla throughout his life. His unusual behaviors, his intense focus on his internal world, and his inability to relate to other children made him an outsider. He formed few friendships and often preferred the company of books and his own imagination to that of his classmates. His teachers recognized his genius, but also noted his peculiar habits and his tendency toward what they described as nervous exhaustion. The family's financial situation was precarious, and there were serious questions about whether they could afford to provide Nikola with the advanced education his abilities clearly warranted. Milutin Tesla earned a modest salary as a priest, and the family lived simply in a small house with minimal furnishings. Every decision about Nikola's education required careful consideration of the financial implications. When Nikola was 10 years old, the family made a crucial decision that would shape the rest of his life. They sent him to the higher real gymnasium in Karlovac, Croatia, to live with his aunt and uncle and receive a more advanced education than was available in their small village. This separation from his family was difficult for the sensitive boy, but it also opened up new intellectual horizons that fed his hungry mind. The gymnasium in Karlovac was a significant step up from the village school in Smiljan. Here, Nikola encountered teachers who recognized and nurtured his exceptional abilities. He excelled in mathematics, physics, and languages, quickly mastering German, French, and Italian in addition to his native Serbian. His physics teacher, Professor Poschel, became particularly important in Nikola's development, introducing him to advanced concepts in mechanics and electrical theory. It was during his time in Karlovac that Nikola first encountered demonstrations of electrical phenomena that would captivate his imagination for the rest of his life. The school had acquired a primitive electrical generator, and young Tesla was mesmerized by the sparks and electrical discharges it produced. He spent countless hours studying the device, trying to understand the principles behind its operation, and beginning to formulate his own theories about the nature of electricity. But even as his intellectual abilities flourished, Tesla's personal challenges intensified. The pressure to excel, combined with his natural perfectionism and the memory of his deceased brother's legacy, drove him to work with an intensity that bordered on self-destruction. He would study for 18 or 20 hours a day, pushing his body and mind to their limits, often collapsing from exhaustion. His health began to suffer under this relentless pressure. He developed what his doctors described as nervous disorders, experiencing strange visions and hallucinations that would come and go unpredictably. Sometimes he would see flashes of light before his eyes that were so bright they interfered with his vision. Other times he would hear sounds that weren't there, or feel sensations of touch when nothing was touching him. Despite these challenges, Tesla's academic performance remained extraordinary. He completed the 4-year program at the gymnasium in only 3 years, graduating in 1873 with the highest honours. His teachers unanimously agreed that he possessed one of the most brilliant minds they had ever encountered, and they strongly recommended that he continue his education at the university level. But as Tesla prepared to leave Karlovac and return to his family, a crisis was brewing that would test everything he had learned about himself and his capabilities. His father had decided that Nikola should follow in his footsteps and become a priest, a decision that filled the young man with dread. Tesla had no interest in religious life and was determined to pursue his passion for science and engineering, but defying his father's wishes would require a courage he wasn't sure he possessed. The confrontation between father and son was inevitable, and it came to a head during the summer of 1873 when Nikola returned home to Smiljan. Milutin Tesla had made his decision based on practical considerations that made perfect sense to a man of his generation and circumstances. The priesthood offered stability, respect within the community, and a guaranteed income. For a family of modest means living in a politically unstable region, these were not trivial concerns. But for Nikola, the prospect of dedicating his life to religious service felt like a form of spiritual death. His mind was alive with visions of mechanical devices, electrical phenomena, and scientific discoveries. The idea of spending his days conducting religious ceremonies and providing pastoral care held no appeal whatsoever. He had discovered his true calling in the realm of science and technology, and he was prepared to fight for the right to pursue it. The argument that ensued was perhaps the most important conversation of Tesla's young life. Father and son faced each other across the small living room of the family home, each convinced of the righteousness of his position. Milutin spoke of duty, tradition, and the practical realities of making a living in an uncertain world. Nikola spoke of passion, innovation, and the calling he felt to push the boundaries of human knowledge. The debate might have continued indefinitely, but fate intervened in the form of a cholera epidemic that swept through the region in the late summer of 1873. Nikola contracted the disease and became gravely ill, spending weeks hovering between life and death. As he lay in bed, Burning with fever and barely conscious, his father sat beside him, watching his brilliant son waste away. It was during one of Nikola's brief moments of lucidity that Milutin made a decision that would change everything. Seeing his son's condition and recognizing how desperately the young man wanted to pursue his scientific studies, the priest leaned close to his son's ear and whispered a promise. If Nikola would fight to recover, if he would find the strength to overcome this illness, then his father would support his decision to study engineering rather than enter the priesthood. The effect of this promise on Tesla's recovery was immediate and remarkable. Within days, his fever broke, his strength began to return, and his will to live was fully restored. He had won the right to pursue his dreams, but the cost had been enormous. The illness left him weakened and changed, more sensitive than ever to physical stimuli and prone to the nervous disorders that would plague him for the rest of his life. As 1874 dawned, Tesla faced a new challenge. Austrian law required all young men to serve 3 years of military service, and his name had been called for conscription. The prospect of military life filled him with horror. His sensitive nature, his unusual habits, and his intense focus on intellectual pursuits made him utterly unsuited for the rigid discipline and physical demands of army life. He was convinced that military service would destroy his health and end his chances of pursuing higher education. With his father's reluctant blessing, Tesla fled to the mountains of his homeland to avoid conscription. He spent nearly a year living as a fugitive in the wild regions of the Velebit mountain range, hiding from authorities and living off the land. This period of exile, while terrifying and difficult, also proved to be transformative. Away from the pressures of family expectations and social conventions, Tesla had the freedom to think, to explore his ideas, and to strengthen his body through outdoor exercise. During his months in the mountains, Tesla's physical health improved dramatically. The fresh air, regular exercise, and simple living helped him overcome many of the nervous symptoms that had plagued him since childhood. He spent his days hiking through forests, swimming in mountain streams, and reading books he had brought with him into exile. Most importantly, he had unlimited time to develop his mental laboratory, refining his ability to visualize and test mechanical devices entirely in his imagination. The mountain exile also gave Tesla time to plan his future with unprecedented clarity. He knew exactly what he wanted to study and where he wanted to study it. The Austrian Polytechnic Institute in Graz had one of the finest engineering programs in Europe, and Tesla was determined to gain admission. He spent hours each day studying mathematics and physics, preparing himself for the challenges that lay ahead. When Tesla finally emerged from the mountains in 1875, he had been transformed from a sickly, nervous young man into a physically robust and mentally focused individual ready to take on the world. His father had managed to arrange for his military service to be deferred, and the family had scraped together enough money to pay for his first year at the Polytechnic. Everything seemed aligned for Tesla's academic success. The Austrian Polytechnic Institute in Graz was a revelation for the young Tesla. Here was an institution dedicated entirely to scientific and technical education, filled with professors who shared his passion for understanding how the world worked. The curriculum was rigorous and comprehensive, covering mathematics, physics, chemistry, and various branches of engineering. For the first time in his life, Tesla found himself in an environment where his unusual intellectual gifts were not just tolerated, but actively encouraged. Tesla threw himself into his studies with characteristic intensity. He attended lectures from early morning until late at night, often staying in the laboratory until the building was locked for the evening. His professors were amazed by his ability to absorb complex mathematical concepts and his intuitive understanding of physical principles. He could solve problems that stumped his classmates and often found errors in textbooks that had gone unnoticed for years. But it was during his second year at Graz that Tesla encountered the demonstration that would change the course of his life forever. Professor Poeschl, his physics instructor, had acquired a new piece of equipment called a Grammar dynamo, one of the latest developments in electrical generation technology. The device was impressive in its operation, but it had one significant flaw that bothered Tesla immensely. The Grammar dynamo operated using direct current and required the use of brushes and a commutator to change the direction of current flow. These mechanical components created sparks during operation, generated heat, and wore out quickly, requiring frequent maintenance and replacement. As Tesla watched the sparks fly from the machine during Professor Poeschl's demonstration, his mind began working on the problem. After class, Tesla approached his professor with a suggestion. What if it were possible to eliminate the brushes and commutator entirely by using alternating current instead of direct current? The rotating magnetic field could be created electrically rather than mechanically, eliminating the need for the troublesome mechanical components. Professor Poeschl's response was swift and dismissive. He explained to Tesla in front of the entire class that such an idea was impossible. The laws of physics, he declared, made it clear that a motor could not operate without brushes and a commutator. Tesla's suggestion was not just impractical, it was theoretically impossible, and the young man would be wise to focus his attention on more realistic problems. The public humiliation stung, but it also ignited something deeper in Tesla's mind. He became obsessed with proving his professor wrong, spending every spare moment thinking about the problem of creating a motor that operated on alternating current. He filled notebook after notebook with calculations and diagrams, testing various configurations in his mental laboratory. For months, Tesla struggled with the problem, making little progress despite his intense focus. The mathematical challenges were enormous and the physical principles involved were at the very edge of contemporary understanding. There were moments when he began to doubt himself, wondering if Professor Poeschl might have been correct after all. The breakthrough came in February of 1882, not in a laboratory or lecture hall, but during a walk through the city park in Budapest with his friend Antoni Szigeti. Tesla was reciting lines from Goethe's Faust when suddenly, mid-sentence, he stopped walking and stood perfectly still. His mind had just grasped the solution to the alternating current motor problem with stunning clarity. In that moment of inspiration, Tesla saw the complete design for a polyphase system of alternating current motors and generators. He could visualize the rotating magnetic field, understand how it could be created using multiple phases of alternating current, and see exactly how such a system would eliminate the need for brushes and commutators. The vision was so clear and complete that he could mentally test the operation of every component. Szigeti watched in amazement as his friend stood motionless in the park, his eyes bright with excitement, his mind clearly working through some complex problem. When Tesla finally spoke, it was to describe in rapid, enthusiastic detail a revolutionary electrical system that would transform the world. But first, he would need to build it, test it, and prove that his vision was more than just an elaborate fantasy. The next several years would test Tesla's resolve, his patience, and his faith in his own abilities. He would face rejection, ridicule, and financial hardship as he tried to bring his revolutionary ideas to life. But he would also find allies, opportunities, and eventually the chance to prove that the impossible motor he had envisioned in a Budapest park was not only possible, but destined to power the modern world. The years following Tesla's revelation in Budapest were a study in frustration and determination. Armed with the complete mental blueprint for his alternating current motor, Tesla faced the harsh reality that having a revolutionary idea and bringing it to fruition were entirely different challenges. He needed resources, equipment, and most importantly, someone who would believe in his vision enough to invest in its development. Tesla's first opportunity came through a position with the Central Telegraph Company in Budapest, where he worked under Tivadar Puskas, a Hungarian inventor and entrepreneur who had connections throughout European engineering circles. The job was supposed to involve improving telephone equipment, but Tesla found the work mundane compared to the electrical revolution churning in his mind. He performed his duties competently, but spent every spare moment refining his alternating current designs and searching for an opportunity to build working prototypes. During this period, Tesla's peculiar habits and intense focus began to concern his colleagues. He would often work through the night, forgetting to eat or sleep as he became absorbed in his calculations. His hypersensitive nervous system made him react strongly to unexpected sounds or physical contact, leading some to whisper that the brilliant young engineer might be losing his mind. Tesla was aware of these concerns but felt powerless to change his nature. The same mental intensity that allowed him to visualize complex machines also made him vulnerable to overstimulation and exhaustion. In 1883, Puskas arranged for Tesla to transfer to Paris, where he would work for the Continental Edison Company under Charles Batchelor, Thomas Edison's representative in Europe. This move would prove pivotal in Tesla's career, though not in ways he initially anticipated. Paris was the centre of European electrical development, and the Edison Company was at the forefront of direct current electrical systems that were beginning to illuminate cities across the continent. The Continental Edison Company occupied impressive offices on the Avenue de l'Opéra, and Tesla was immediately struck by the scale of the operation. Here were dozens of engineers and technicians working on practical electrical applications, from lighting systems to motors to generators. For the first time since leaving Graz, Tesla found himself surrounded by people who shared his passion for electrical technology, even if they didn't share his specific vision for alternating current. Charles Batchelor was a practical man with little patience for theoretical discussions, but he quickly recognized Tesla's exceptional abilities. The young Serbian engineer could diagnose electrical problems that stumped experienced technicians, and his mathematical skills were far superior to those of his colleagues. Within months, Tesla had become Batchelor's most trusted troubleshooter, dispatched to solve the most challenging technical problems that arose in Edison installations across France and Germany. These field assignments gave Tesla invaluable experience with real-world electrical systems and their limitations. He saw firsthand how direct current systems struggled with power transmission over long distances, requiring power stations to be built every few miles to maintain adequate voltage. He observed the constant maintenance problems caused by brushes and commutators in Edison's motors and generators. Every problem he encountered reinforced his conviction that alternating current offered superior solutions, if only someone would give him the chance to prove it. Tesla's reputation for solving impossible problems grew throughout the Edison organization, but his suggestions for fundamental improvements were consistently dismissed. When he proposed modifications to generator designs that could increase efficiency by 20%, his supervisors showed polite interest, but no inclination to implement changes to proven systems. When he mentioned his ideas for alternating current motors, he was told that the Edison Company was committed to direct current and had no interest in pursuing alternative approaches. The frustration was maddening for Tesla, who could see clearly how electrical technology could be revolutionized, but found himself trapped in an organization dedicated to incremental improvements rather than fundamental breakthroughs. He began to understand that bringing his vision to reality would require more than technical expertise. He would need to navigate corporate politics, financial considerations, and the conservative instincts of established businesses. During his time in Paris, Tesla also experienced his first taste of the fierce commercial competition that characterized the electrical industry. The Edison Company was locked in battles with gas lighting companies, competing electrical manufacturers, and inventors trying to develop superior technologies. Patents were fiercely guarded, trade secrets were closely held, and commercial success often depended as much on marketing and political influence as on technical merit. Tesla watched these commercial battles with the fascination of an outsider trying to understand a foreign culture. His mind was focused on pure innovation, on pushing the boundaries of what was scientifically possible, but he began to realize that success in the electrical industry required skills he had never developed. He would need to learn about business, about patents, about the complex relationships between inventors, investors, and manufacturers. The opportunity Tesla had been waiting for came in early 1884 when Charles Batchelor decided to return to New York and invited Tesla to join him at Edison's main operations in America. Batchelor had been impressed by Tesla's abilities and believed that Edison himself would appreciate the young engineer's talents. He provided Tesla with a letter of introduction that would prove to be one of the most important documents in the history of electrical engineering. The letter was brief, but compelling in its praise. Batchelor wrote that he knew two great men, and Tesla was one of them. The other, he implied, was Edison himself. This introduction would open the door to Tesla's next chapter, but it would also set the stage for one of the most famous conflicts in scientific history. As Tesla prepared to leave Paris for New York, he felt a mixture of excitement and apprehension. America represented opportunity on a scale that Europe couldn't match, but it also represented the unknown. He would be leaving behind the familiar world of European engineering culture for a country known for its entrepreneurial energy, but also its ruthless business practices. Tesla arrived in New York Harbor in June 1884 with 4 cents in his pocket, a few personal belongings, and the complete plans for his alternating current system stored in his prodigious memory. The city that greeted him was unlike anything he had ever experienced. New York was growing at an explosive pace, with construction projects everywhere, and an energy that seemed to match his own inner intensity. The Edison Machine Works occupied several buildings on Goeck Street on the Lower East Side, and Tesla was immediately impressed by the scale of American manufacturing. Here were machine shops, assembly lines, and testing facilities that dwarfed anything he had seen in Europe. Hundreds of workers were building dynamos, motors, and electrical components that would power the rapidly expanding electrical infrastructure of American cities. Thomas Edison himself was 47 years old when Tesla arrived at his laboratories, already famous as the inventor of the incandescent light bulb and the phonograph. Edison was everything Tesla was not, practical rather than theoretical, focused on immediate commercial applications rather than fundamental scientific principles, and supremely confident in his ability to solve any problem through persistent experimentation rather than mathematical analysis. The two men could hardly have been more different in their approaches to invention. Edison famously declared that genius was 1% inspiration and 99% perspiration, believing that systematic trial and error would eventually solve any technical challenge. Tesla, by contrast, relied on his mental laboratory to perfect his designs before ever building a physical prototype, considering Edison's approach wasteful and inefficient. Despite these fundamental differences, Edison was impressed by Tesla's abilities and put him to work immediately on some of the most challenging problems facing the Edison company. Tesla's first major assignment was to redesign Edison's direct current generators to improve their efficiency and reduce production costs. It was exactly the kind of practical problem that played to Tesla's strengths, while keeping him focused on direct current technology rather than his alternating current ideas. Tesla attacked the generator problem with characteristic intensity, working 18-hour days and applying his mathematical skills to optimize every aspect of the design. Within months, he had developed improvements that significantly increased the efficiency of Edison's generators while reducing the amount of material required for their construction. The modifications were so successful that they saved the company substantial amounts of money and enhanced the performance of installations across the Edison system. Edison was delighted with Tesla's work and began giving him increasingly important assignments. Tesla redesigned motors, improved arc lighting systems, and solved technical problems that had stumped Edison's other engineers for months. His reputation within the company grew rapidly, and Edison began to rely on him as his most capable problem solver. But beneath the surface of this successful working relationship, tensions were building. Tesla chafed at being confined to incremental improvements of direct current technology when he knew that alternating current offered far superior solutions. He had tried several times to interest Edison in his alternating current motor designs, but Edison dismissed them with barely concealed contempt. Edison's hostility to alternating current was not merely technical, but also commercial. He had invested enormous amounts of time, money, and reputation in developing direct current systems. His company had installed direct current electrical networks in cities across America and Europe. Acknowledging that alternating current was superior would mean admitting that his life's work was based on an inferior technology. The conflict between Tesla and Edison came to a head in late 1884 over a seemingly routine project. Edison had challenged Tesla to redesign the company's generators completely, promising a bonus of $50,000 if Tesla could achieve specific improvements in efficiency and cost reduction. It was an enormous sum, equivalent to more than $1 million in today's money, and Tesla accepted the challenge eagerly. Working with obsessive dedication, Tesla completely reimagined Edison's generator designs, applying advanced mathematical analysis to optimize every component. His new designs were revolutionary, incorporating innovations that improved efficiency far beyond what Edison had requested, while actually reducing manufacturing costs. When Tesla presented his completed work, even Edison was forced to admit that the improvements exceeded his highest expectations. But when Tesla requested his promised bonus, Edison's response revealed the gulf between the two men's characters. With a smile that Tesla would remember for the rest of his life, Edison dismissed the bonus as a joke, telling Tesla that he didn't understand American humor. The $50,000 had never been serious, Edison claimed, and Tesla would have to be satisfied with a modest salary increase instead. Tesla was devastated, not just by the loss of the money, but by the betrayal of trust. He had given Edison his best work, had solved problems that seemed impossible, and had been repaid with deception and mockery. The incident crystallized everything that Tesla disliked about American business culture. The emphasis on immediate profit over long-term innovation, the willingness to exploit talented individuals, and the casual dishonesty that passed for shrewd negotiation. The break between Tesla and Edison was swift and final. Within days of Edison's refusal to pay the promised bonus, Tesla submitted his resignation and walked out of the Edison machine works forever. He was 30 years old, virtually penniless, and had just severed his relationship with the most powerful figure in the American electrical industry. But he was also free for the first time since arriving in America to pursue his own vision of electrical technology. Tesla's departure from Edison's company marked the beginning of the most difficult period of his American experience. Without Edison's backing or the resources of an established company, Tesla found himself struggling to survive in a city that showed little mercy to failed entrepreneurs. He had brilliant ideas but no way to implement them, revolutionary designs but no access to manufacturing facilities, and scientific knowledge that seemed worthless without commercial backing. For nearly a year, Tesla lived in poverty, taking whatever work he could find to pay for basic necessities. He dug ditches, repaired electrical equipment, and even worked as a common labourer on construction projects. The man who had redesigned Edison's generators was reduced to physical labor, but he refused to abandon his vision of alternating current technology. Even while swinging a shovel or carrying materials, his mind continued to refine and improve his motor designs. The darkest period of Tesla's life was also a time of profound character development. The humiliation of manual labor taught him humility and resilience, while the financial pressure forced him to think seriously about the commercial aspects of invention. He began to understand that brilliant ideas alone were not enough, that bringing revolutionary technology to market required business skills, financial backing, and political savvy. It was during this period of struggle that Tesla met the man who would become his first true ally in America. Alfred S. Brown was a successful businessman who had made his fortune in the telegraph industry and was looking for investment opportunities in the rapidly expanding field of electrical technology. Brown had heard rumors about a brilliant Serbian inventor who claimed to have solved the alternating current motor problem, and his curiosity was piqued enough to arrange a meeting. The meeting between Tesla and Brown took place in a small office near Wall Street in the spring of 1887. Tesla arrived carrying nothing but his worn leather portfolio containing hand-drawn diagrams of his alternating current system. He was thin from months of poor nutrition, his clothes were patched and faded, but his eyes burned with an intensity that immediately captured Brown's attention. When Tesla began to describe his motor designs, speaking with passionate precision about rotating magnetic fields and polyphase systems, Brown realized he was listening to something extraordinary. Brown was not an engineer himself, but he had spent decades evaluating technical innovations for their commercial potential. He understood that truly revolutionary technologies often came from unexpected sources, and Tesla's alternating current motor seemed to offer solutions to problems that had plagued the electrical industry since its inception. The elimination of brushes and commutators alone would represent a massive improvement in efficiency and reliability. But Brown was also a cautious businessman who had seen many brilliant inventors fail because they lacked practical experience with manufacturing and marketing. Tesla's ideas were impressive, but could they be built? Could they compete with established direct current systems? And most importantly, could they generate profits for investors willing to take the risk? To answer these questions, Brown arranged for Tesla to demonstrate his motor designs to a small group of potential investors and technical experts. The demonstration took place in a cramped laboratory that Brown had rented specifically for the occasion. Tesla had spent weeks preparing, using his meager savings to purchase the materials needed to build working prototypes of his alternating current motors. The demonstration itself was a masterpiece of technical theatre. Tesla had constructed several different motor configurations, each designed to illustrate a specific aspect of his alternating current system. He explained the theoretical principles behind rotating magnetic fields, showed how polyphase currents could be generated and transmitted, and demonstrated the smooth, efficient operation of motors that required no brushes or commutators. The audience watched in fascination as Tesla's motors ran silently and efficiently, their rotating magnetic fields invisible but clearly effective. When Tesla reversed the direction of rotation, simply by switching two of the electrical connections, several observers gasped in amazement. Direct current motors required mechanical modifications to change direction, but Tesla's alternating current motors could be controlled electrically with simple switches. Among the observers that day was Charles Peck, a prominent attorney and businessman who specialized in patent law and technology investments. Peck understood immediately that Tesla's motor designs represented potentially valuable intellectual property, but he also recognized the challenges involved in bringing such revolutionary technology to market. The electrical industry was dominated by established companies with enormous investments in direct current systems, and they would not welcome competition from alternating current technology. After lengthy discussions and careful evaluation of Tesla's designs, Brown and Peck made a decision that would change the course of electrical history. They offered to form a partnership with Tesla, providing the financial backing and business expertise needed to develop his alternating current system in exchange for a share of any profits that might result. The Tesla Electric Company was officially incorporated in April 1887, with Tesla holding the rights to his inventions while Brown and Peck provided capital and management. The formation of the Tesla Electric Company marked the beginning of the most productive period of Tesla's career. For the first time since arriving in America, he had access to proper laboratory facilities, skilled assistants, and the financial resources needed to build and test his inventions. The company rented space in a building on South Fifth Avenue that Tesla quickly transformed into a state-of-the-art electrical laboratory. Tesla's approach to invention was unlike anything his new partners had ever witnessed. Where other inventors relied on trial and error, building prototype after prototype, until something worked, Tesla would spend weeks perfecting his designs mentally before ever touching a piece of equipment. When he finally did build a physical device, it typically worked perfectly on the first attempt, requiring little or no modification. This mental methodology allowed Tesla to develop multiple inventions simultaneously, switching his attention from motors to generators to transmission systems as inspiration struck. Within months of the company's formation, Tesla had created working prototypes of an entire alternating current system, from generators that produced polyphase currents to motors that converted those currents back into mechanical power. But developing the technology was only the beginning of the challenge. Tesla's alternating current system would need to be protected by patents, manufactured efficiently, and marketed against the entrenched opposition of the direct current establishment. The patent applications alone required months of careful preparation, as Tesla's inventions were so novel that existing patent categories could barely accommodate them. Charles Peck proved invaluable in navigating the complex world of patent law. He understood that Tesla's motor designs represented not just single inventions but an entire system of related technologies that could be protected by multiple patents. The strategy was to file broad claims that would prevent competitors from developing similar systems, while also filing specific claims that protected particular innovations within the overall design. The patent applications revealed the full scope of Tesla's genius to the technical community for the first time. His polyphase motor system included innovations in generator design, motor construction, power transmission, and electrical control that collectively represented the most significant advance in electrical technology since Edison's incandescent lamp. When the patents were finally granted in May 1888, they established Tesla as one of the premier electrical inventors in America. But patents were worthless without commercial applications, and Tesla's partners understood that demonstrating the practical value of alternating current would require more than laboratory prototypes. They needed to show that Tesla's motors could perform real work under industrial conditions, competing directly with the established direct current systems that powered factories and workshops across the country. The opportunity for such a demonstration came through the American Institute of Electrical Engineers, which invited Tesla to present a lecture on his alternating current system at their annual meeting in New York. The presentation, delivered on May 16, 1888, would prove to be one of the most important technical lectures in the history of electrical engineering. Tesla's lecture was a tour de force of scientific exposition and practical demonstration. He explained the theoretical principles behind rotating magnetic fields in language that both engineers and laypeople could understand, then demonstrated working motors that proved his theories correct. The audience watched in amazement as Tesla's motors operated with a smoothness and efficiency that direct current motors simply could not match. The response to Tesla's lecture was immediate and dramatic. Electrical engineers who had dismissed alternating current as impractical suddenly recognized its revolutionary potential. Investors who had been skeptical about Tesla's claims began to see the enormous commercial opportunities that his technology represented. And most importantly for Tesla's future, representatives of major electrical companies began to express serious interest in acquiring his patents. Among those in the audience that night was a representative of the Westinghouse Electric Company, one of Edison's primary competitors in the rapidly expanding electrical industry. George Westinghouse had built his company on innovations in railroad technology, but he had recently begun investing heavily in electrical equipment and was looking for technologies that could give his company a competitive advantage over Edison's direct current systems. Westinghouse understood immediately that Tesla's alternating current technology offered exactly the breakthrough his company needed. While Edison's direct current systems were limited to serving customers within a few miles of generating stations, Tesla's alternating current could be transmitted over much greater distances using transformers to step voltage up for efficient transmission and back down for safe utilization. The commercial implications were staggering. An electrical company using Tesla's technology could serve customers across entire cities from a single generating station, dramatically reducing the infrastructure costs that made electrical service expensive and limiting its adoption. Alternating current offered the possibility of bringing electrical power to rural areas that could never be served economically by direct current systems. Within days of Tesla's lecture, Westinghouse contacted the Tesla Electric Company to inquire about acquiring the rights to Tesla's alternating current patents. The negotiations that followed would determine not only Tesla's personal fortune, but also the fundamental nature of electrical power systems for the next century and beyond. The initial meetings between Tesla and Westinghouse revealed two men with very different personalities, but complementary visions. Westinghouse was a practical businessman who understood that technological superiority meant nothing without market success, while Tesla was a pure inventor who cared more about seeing his ideas implemented than about personal profit. Both men recognized that Tesla's alternating current system represented a revolutionary advance, but they differed on how best to bring that revolution to market. Westinghouse's offer was generous by any measure. He proposed to purchase Tesla's alternating current patents for $1 million in cash, plus royalty payments of $1 for every horsepower of alternating current equipment sold using Tesla's designs. The total value of the deal could potentially reach tens of millions of dollars if alternating current achieved widespread adoption. For Tesla, who had been digging ditches just a year earlier, the offer represented financial security beyond his wildest dreams. But more importantly, it offered the chance to see his inventions implemented on a scale that would transform the electrical industry. Westinghouse commanded the resources needed to manufacture alternating current equipment in large quantities, and the marketing expertise needed to compete with Edison's established direct current systems. The contract negotiations were complex, involving not just the purchase price, but also Tesla's role in developing the technology further. Westinghouse wanted Tesla to join his company as a consulting engineer, helping to refine the alternating current system for mass production and training Westinghouse engineers in its operation. Tesla was eager to continue his inventive work, but worried about losing control over the direction of his technology's development. After weeks of discussion, the final agreement was signed in July 1888. Tesla received his $1 million payment and agreed to work with Westinghouse to develop alternating current technology for commercial applications. The deal made Tesla wealthy beyond his previous imagination, but more importantly, It set the stage for the epic battle between alternating and direct current that would reshape the electrical industry. The partnership between Tesla and Westinghouse began with high hopes on both sides, but it quickly became apparent that combining revolutionary technology with commercial manufacturing presented unexpected challenges. Tesla's designs, while technically brilliant, had been optimized for laboratory demonstrations rather than mass production. Adapting them for factory manufacturing required compromises that Tesla found personally painful. Tesla spent months at Westinghouse's facilities in Pittsburgh, working with company engineers to modify his motor designs for practical applications. The process was frustrating for a man accustomed to working alone, as every change required consensus among multiple engineers and approval from company managers who prioritized cost reduction over technical perfection. But the collaboration also exposed Tesla to aspects of electrical engineering that his theoretical background had not prepared him for. He learned about the practical constraints of manufacturing, the importance of standardization, and the need to design systems that could be operated and maintained by ordinary technicians rather than brilliant inventors. Meanwhile, Thomas Edison had learned of Tesla's partnership with Westinghouse and recognized the threat that alternating current posed to his direct current empire. Edison's response would be swift, ruthless, and ultimately counterproductive, launching a campaign against alternating current that would become known as the War of the Currents and would determine the future of electrical power in America. The future of electrical power in America? The War of the Currents began not with technical arguments, but with a propaganda campaign that would define corporate warfare for generations to come. Edison understood that Tesla's alternating current system was technically superior to his direct current infrastructure, but he also knew that public perception could be more powerful than engineering reality. If he could convince the American public that alternating current was dangerous, he might preserve his electrical empire even in the face of superior technology. Edison's strategy was as brilliant as it was ruthless. He began a systematic campaign to associate alternating current with death and danger, staging public demonstrations designed to terrify audiences and turn them against Westinghouse's technology. Edison's laboratories became theatres of electrical horror, where company representatives would electrocute animals using alternating current while emphasizing that direct current at the same voltages was harmless. The most infamous of these demonstrations involved the electrocution of elephants, dogs, and other animals using Tesla's alternating current technology. Edison's assistants would carefully explain to horrified audiences that the animals died instantly because alternating current was inherently more dangerous than direct current. What they failed to mention was that any electrical current at sufficiently high voltage could be lethal, and that the demonstrations used voltages far higher than anything found in practical electrical systems. Edison's campaign reached its peak with his involvement in the development of the electric chair. When the state of New York decided to replace hanging with a more humane method of execution, Edison secretly provided technical assistance to ensure that the electric chair would use alternating current. His goal was to create a permanent association in the public mind between alternating current and death. The first execution by electric chair, carried out in August 1890, was a gruesome affair that seemed to validate Edison's claims about the dangers of alternating current. The condemned man, William Kemmler, did not die instantly as planned, but survived the first electrical shock and had to be electrocuted a second time. Newspapers across the country reported the botched execution in horrifying detail, exactly as Edison had hoped. Tesla watched Edison's propaganda campaign with a mixture of disgust and fascination. He understood that Edison was deliberately misleading the public about the relative safety of different electrical systems, but he also recognized the effectiveness of Edison's tactics. Public opinion was turning against alternating current despite its technical advantages, and Westinghouse's business was beginning to suffer. The pressure on Westinghouse intensified when several cities that had been considering alternating current systems decided to stick with Edison's direct current technology. The financial impact was enormous, as Westinghouse had invested millions of dollars in manufacturing facilities designed to produce alternating current equipment. If the market for that equipment disappeared, the company faced potential bankruptcy. Tesla felt personally responsible for Westinghouse's difficulties, even though Edison's propaganda campaign was based on deliberate distortions of scientific fact. He had created the technology that was now being demonized, and he watched helplessly as his revolutionary inventions were portrayed as instruments of death and destruction. But Tesla also began to understand something important about the relationship between technology and society. Pure technical merit was not enough to ensure success in the commercial marketplace. Public perception, political influence, and marketing skill could be just as important as engineering excellence in determining which technologies would ultimately prevail. The turning point in the War of the Currents came from an unexpected source. The organizers of the 1893 World's Columbian Exposition in Chicago were looking for a company to provide electrical lighting for the fair, which was expected to attract millions of visitors from around the world. The contract would be enormous, requiring the installation of more electrical equipment than had ever been assembled in a single location. Both Edison's General Electric Company and Westinghouse's company submitted bids for the lighting contract. Edison proposed using direct current technology that would require dozens of generating stations scattered throughout the fairgrounds to maintain adequate voltage. Westinghouse proposed using Tesla's alternating current system with transformers that could distribute power efficiently from a few central generating stations. The difference in cost was dramatic. Westinghouse's alternating current system could illuminate the entire exposition for less than half the cost of Edison's direct current proposal. Despite Edison's propaganda campaign, the exposition organizers were more interested in practical economics than theoretical safety concerns. They awarded the contract to Westinghouse, giving Tesla's technology its first major public showcase. The World's Columbian Exposition opened in May 1893 to crowds that exceeded all expectations. Visitors from across America and around the world marveled at the electrical displays that turned night into day throughout the fairgrounds. Tesla's alternating current system performed flawlessly, providing reliable power to thousands of lights, motors, and electrical devices without a single serious accident. The success of the exposition's electrical system provided powerful evidence that alternating current was not only safe, but superior to direct current for large-scale applications. Newspapers that had previously echoed Edison's safety concerns began to report favourably on the smooth operation of Westinghouse's equipment. Public opinion slowly began to shift as people saw alternating current working reliably in the most visible electrical installation in the world. But the ultimate victory in the War of the Currents would come from an even more spectacular demonstration of alternating current's capabilities. The Niagara Falls Power Company was planning to build the world's largest hydroelectric generating station, harnessing the enormous power of Niagara Falls to provide electricity to cities hundreds of miles away. The scale of the project was unprecedented, and the choice between alternating and direct current technology would determine the future of electrical power in America. The Niagara project presented exactly the kind of challenge that showcased alternating current's greatest advantage. Direct current could not be transmitted efficiently over the long distances required to serve distant cities, while Tesla's alternating current system could use transformers to step voltages up for efficient long-distance transmission and back down for safe local distribution. Tesla became personally involved in designing the Niagara generating station, working with Westinghouse engineers to create the most advanced electrical installation ever attempted. The generators would produce polyphase alternating current at frequencies and voltages that had never been used in commercial applications. The transmission system would carry electrical power farther than any previous installation. The technical challenges were enormous, requiring innovations in generator design, transmission line construction, and electrical control systems. Tesla's mental laboratory worked overtime as he visualized solutions to problems that had never been encountered before. Every aspect of the system had to be designed from scratch, as no existing technology could handle the power levels and transmission distances involved. Construction of the Niagara generating station began in 1893 and continued for 3 years. Tesla made frequent trips to the construction site, supervising the installation of equipment and solving technical problems as they arose. He was fascinated by the scale of the project and energized by the opportunity to see his alternating current system implemented at its full potential. When the Niagara station began operation in November 1896, it represented the complete vindication of Tesla's alternating current technology. Electrical power generated by the falling water was transmitted successfully to Buffalo, 25 miles away, demonstrating that alternating current could serve cities far from generating stations. The success of Niagara marked the end of the War of the Currents and the beginning of the alternating current age. Edison's direct current systems would continue to operate in some locations for several more decades, but the fundamental battle had been decided. Alternating current offered such overwhelming advantages for power transmission and distribution that its eventual dominance was inevitable. Tesla's vision, born in a Budapest park more than a decade earlier, had finally been proven correct on the largest possible stage. The success of the Niagara project made Tesla internationally famous and established him as one of the premier electrical inventors of his generation. But fame and fortune also brought new pressures and expectations that would challenge Tesla's unconventional personality in unexpected ways. The man who had struggled for recognition now found himself overwhelmed by attention from investors, journalists, and fellow inventors who wanted to share in his success. Tesla's newfound celebrity status opened doors that had previously been closed to him, but it also created demands on his time and energy that interfered with his inventive work. He was invited to lecture at universities, consulted by major corporations, and sought out by wealthy individuals who hoped to invest in his next revolutionary technology. The quiet laboratory work that he preferred was increasingly interrupted by social and professional obligations. More challenging for Tesla was the realization that his financial success had not brought him the satisfaction he had expected. The millions of dollars he had earned from his alternating current patents provided security and freedom, but they did not eliminate the restless energy that drove his constant invention. If anything, financial independence made Tesla more aware of how little material wealth meant to him compared to the thrill of technological discovery. Tesla began to feel constrained by his association with Westinghouse and the commercial electrical industry. His alternating current patents were generating enormous royalty payments, but they also tied him to a specific technology at a time when his mind was racing ahead to entirely new concepts. He was becoming known as the alternating current inventor when he wanted to be recognized as a pioneer of technologies that had not yet been imagined. The tension between Tesla's inventive impulses and his commercial obligations came to a head during the economic crisis of 1893. The financial panic that swept through the American economy put enormous pressure on companies like Westinghouse, which had borrowed heavily to finance the expansion of their alternating current manufacturing capabilities. Westinghouse found himself unable to pay the royalties owed to Tesla under their original agreement, threatening both the company's survival and Tesla's income. Tesla faced a crucial decision that would reveal much about his character and priorities. He could insist on full payment of his royalties, potentially forcing Westinghouse into bankruptcy and destroying the company that had made his alternating current system commercially viable. Or he could sacrifice his financial interests to preserve the partnership that had brought his technology to the world. After agonizing consideration, Tesla made a choice that shocked the business community. He voluntarily tore up his royalty contract with Westinghouse, foregoing millions of dollars in future payments to ensure that the company could survive the economic crisis. The decision cost Tesla an estimated $12 million in royalties, an enormous sum that would have made him one of the wealthiest men in America. Tesla's sacrifice saved Westinghouse from bankruptcy and preserved the commercial viability of alternating current technology, but it also freed Tesla from the obligations that had been constraining his inventive work. With his alternating current patents no longer generating royalty income, Tesla needed to find new sources of funding for his research. More importantly, he needed to prove that his genius extended beyond the polyphase motor system that had made him famous. The years following Tesla's break with Westinghouse would see him venture into entirely new realms of scientific investigation. Wireless communication, remote control, and the wireless transmission of power would become his new obsessions, leading him to discoveries and inventions that would be even more revolutionary than his alternating current system. But they would also lead him into conflicts with established scientific opinion and commercial interests that would prove far more challenging than his battle with Edison. Tesla's laboratory on South Fifth Avenue became a wonderland of electrical experimentation as he pursued his new interests with characteristic intensity. He constructed apparatus for generating electrical currents at frequencies never before achieved, created artificial lightning that could be controlled with precision, and began developing theories about the electrical properties of the Earth itself that challenged fundamental assumptions about how electricity behaved. Visitors to Tesla's laboratory were amazed by demonstrations that seemed to defy the laws of physics. Tesla would hold wireless fluorescent lamps that glowed brightly without any visible connection to a power source, or control mechanical devices from across the room using mysterious wireless signals. His experiments suggested possibilities for electrical technology that went far beyond anything the scientific community had previously imagined. But Tesla's new work also isolated him from his former colleagues in the electrical industry, who were focused on refining and expanding the practical applications of alternating current technology. Tesla's interests had moved beyond commercial considerations into pure scientific research, pursuing discoveries that might not have practical applications for decades or even centuries. The man who had revolutionized electrical power was preparing to revolutionize human communication itself, but the path ahead would prove far more difficult than anything he had previously attempted. Tesla was about to enter the most creative and controversial period of his career, a time when his genius would produce innovations that were truly ahead of their time. The period from 1899 to 1905 would mark the height of Tesla's experimental ambition and the beginning of his gradual descent into scientific isolation. During these years, Tesla's mind reached its most creative peak, generating ideas that would not be fully understood or implemented until decades after his death. But these same years also saw him making claims and pursuing projects that stretched the patience of investors and the credibility of the scientific establishment. Tesla's fascination with wireless technology had been growing since his early experiments with high-frequency currents in his New York laboratory. He had observed that electrical energy could be transmitted through space without wires, and his mind immediately grasped the revolutionary implications. If electricity could travel wirelessly, then perhaps all forms of communication and power distribution could be liberated from the constraints of physical connections. The theoretical foundation for Tesla's wireless work rested on his understanding of the Earth as an electrical conductor. Through careful mathematical analysis and experimental observation, Tesla had concluded that the planet itself could serve as a medium for transmitting electrical signals and even electrical power. This concept challenged conventional scientific thinking, which viewed wireless transmission as limited to short distances and low power levels. Tesla's wireless theories were not merely speculative. His laboratory experiments had demonstrated that electrical energy could indeed be transmitted through the ground over considerable distances. He had constructed apparatus that could detect electrical disturbances from hundreds of miles away and had successfully transmitted signals without wires across his laboratory and beyond. The principles were sound, but scaling them to practical applications would require resources and facilities far beyond what his New York laboratory could provide. The opportunity Tesla needed came from an unexpected source. James Gordon Bennett, the wealthy publisher of the New York Herald, had become fascinated by Tesla's wireless experiments and was looking for sensational stories that would capture public attention. Bennett offered to finance Tesla's research in exchange for exclusive rights to report on his discoveries, providing the inventor with both funding and publicity for his most ambitious project yet. With Bennett's backing, Tesla began planning a wireless research station that would dwarf any scientific installation ever constructed. The facility would need to generate electrical power at unprecedented levels, transmit signals across vast distances, and serve as a proving ground for theories that existed nowhere else in the scientific literature. Tesla's mental laboratory had already designed every component of the installation, but bringing it to reality would test his organizational and leadership abilities in ways he had never experienced. Tesla selected Colorado Springs as the location for his wireless experiments, drawn by the area's high altitude, dry climate, and frequent thunderstorms. The thin air would reduce electrical losses, the lack of humidity would improve transmission efficiency, and the natural lightning activity would provide opportunities to study electrical phenomena under conditions that could not be replicated artificially. Most importantly, Colorado Springs was far from the electrical interference of major cities, allowing Tesla to conduct experiments that would be impossible in more populated areas. The laboratory that Tesla constructed in Colorado Springs was unlike anything the scientific world had ever seen. The main building housed a massive electrical generator capable of producing currents at voltages and frequencies that pushed the boundaries of existing technology. A wooden tower rising 200 feet above the laboratory supported a copper sphere that would serve as the terminal for Tesla's wireless transmission experiments. The entire installation was designed to function as a single, enormous electrical instrument. Tesla's arrival in Colorado Springs in May 1899 marks the beginning of the most intensive experimental period of his career. Working with a small team of assistants, he conducted hundreds of experiments designed to test his theories about wireless transmission and the electrical properties of the Earth. His daily routine became a cycle of preparation, experimentation, observation, and analysis that consumed virtually every waking hour. The experiments themselves were spectacular demonstrations of electrical power and control. Tesla's generators could produce artificial lightning bolts more than 100 feet long, creating thunder that could be heard for miles around Colorado Springs. Local residents grew accustomed to the sight of electrical discharges dancing around Tesla's laboratory, and the sound of artificial thunder rumbling across the plains at all hours of the day and night. But behind the dramatic visual displays lay careful scientific work that was advancing human understanding of electrical phenomena in fundamental ways. Tesla was measuring the electrical conductivity of the Earth, mapping the propagation of electrical waves through the ground, and developing techniques for wireless communication that would not be fully appreciated until the development of radio technology decades later. Tesla's most significant discovery during his Colorado Springs period was his detection of what he believed to be electrical signals from outer space. During his experiments with extremely sensitive receiving equipment, Tesla began detecting regular electrical pulses that seemed to come from beyond the Earth's atmosphere. These signals followed patterns that suggested artificial rather than natural origin, leading Tesla to conclude that he was receiving communications from intelligent beings on other planets. The claim that he had detected extraterrestrial signals brought Tesla both international attention and scientific ridicule. While the popular press celebrated his discovery as proof of life on other worlds, the scientific community dismissed his observations as misinterpretation of natural electrical phenomena. Tesla's insistence that the signal showed clear evidence of artificial intelligence only deepened the skepticism of his professional colleagues. Modern analysis suggests that Tesla was probably detecting natural radio emissions from Jupiter and other celestial bodies, phenomena that would not be understood by astronomers until the development of radio telescopy in the mid-20th century. Tesla's equipment was sensitive enough to detect these signals, but the scientific framework for interpreting them did not yet exist. His conclusion that they represented extraterrestrial communication was wrong, but his detection of cosmic radio emissions was a genuine scientific achievement that predated official recognition of such phenomena by more than 40 years. Tesla's wireless experiments in Colorado Springs also led to his development of remote control technology. He constructed small boats that could be operated by wireless signals, demonstrating a level of technological sophistication that amazed observers and hinted at future applications in everything from industrial automation to military systems. These demonstrations were among the first examples of what would later become known as robotics, though Tesla preferred to call his devices teleautomatons. The remote control demonstrations captured public imagination in ways that Tesla's more theoretical work could not. Audiences watched in fascination as Tesla commanded mechanical devices from across a room or even from outside the building, using wireless signals to control their movements with precision. The technology seemed magical to observers who had no framework for understanding how wireless control could be achieved. Tesla understood that remote control technology had enormous commercial and military potential. He envisioned fleets of wireless-controlled ships, aircraft, and vehicles that could perform dangerous tasks without risking human lives. His patents for remote control systems would eventually prove valuable, though the technology would not reach practical application until World War II, decades after Tesla's initial demonstrations. But Tesla's most ambitious goal during his Colorado Springs period was the wireless transmission of electrical power itself. He believed that his experiments had proven that the Earth could serve as a conductor for electrical energy, allowing power to be transmitted to any location on the planet without wires. This concept, which he called his World Wireless System, represented the ultimate expression of Tesla's vision for liberating humanity from the constraints of physical infrastructure. Tesla's power transmission experiments involved sending electrical energy through the ground and retrieving it at distant locations using specially designed receivers. His laboratory notes record successful transmission of electrical power over distances of several miles with efficiency levels that he considered commercially viable. These experiments convinced Tesla that wireless power transmission was not only possible, but inevitable, and he began making plans for a global system that would provide electrical energy to every corner of the Earth. The theoretical basis for Tesla's wireless power transmission rested on his understanding of the Earth as a resonant electrical system. Tesla believed that by exciting the planet's natural electrical resonance, he could establish standing waves that would carry electrical energy efficiently across vast distances. The concept was scientifically sound in principle, though the power levels required for global transmission would prove to be far beyond the capabilities of early 20th century technology. Tesla's experiments with wireless power transmission attracted the attention of financial backers who recognized the enormous commercial potential of such technology. If electrical power could indeed be transmitted wirelessly across continents, the economic implications would dwarf even the alternating current revolution that had made Tesla famous. Investors began approaching Tesla with offers to fund the development of his wireless power system on a commercial scale. The most significant of these offers came from J.P. Morgan, the powerful financier who controlled vast industrial and financial interests across America. Morgan was intrigued by Tesla's claims about wireless communication and power transmission, seeing potential applications that could revolutionize multiple industries simultaneously. After extensive negotiations, Morgan agreed to provide Tesla with the funding needed to construct a commercial wireless transmission facility. Morgan's investment of $150,000 was enormous by the standards of 1900, equivalent to several $1 million in modern terms. But the funding came with conditions that would ultimately prove problematic for Tesla. Morgan expected rapid progress toward commercially viable applications, while Tesla was more interested in perfecting the theoretical foundation of his wireless system. The different expectations would create tensions that would eventually destroy their partnership. With Morgan's backing, Tesla returned to New York and began planning the most ambitious project of his career. He would construct a wireless transmission station on Long Island that would demonstrate the commercial viability of his world wireless system. The facility, which Tesla named Wardenclyffe, would serve as both a proving ground for his theories and a prototype for the global wireless network he envisioned. Tesla selected a site in Shoreham, Long Island, for his Wardenclyffe facility, drawn by its proximity to New York City and its location on the Atlantic coast. The wireless signals would need to cross the ocean to reach European destinations, and Tesla believed that the coastal location would optimize transmission efficiency. He purchased 200 acres of land and began construction of what would become his monument to wireless technology. The centerpiece of Wardenclyffe was a transmission tower that dwarfed even the impressive installation Tesla had built in Colorado Springs. Rising 187 feet above Long Island, the tower was topped with a 55-ton copper sphere designed to serve as the terminal for Tesla's wireless transmissions. The tower itself was anchored by steel shafts driven 120 feet into the ground, creating an electrical connection to the Earth that Tesla considered crucial for his power transmission experiments. The construction of Wardenclyffe consumed Tesla's attention and Morgan's investment throughout 1901 and 1902. Tesla supervised every aspect of the project personally, applying the same perfectionist standards that had characterized all his previous work. No detail was too small to escape his attention, from the precise positioning of electrical components to the aesthetic design of the facility's buildings. But even as construction progressed, Tesla began to realize that the scope of his wireless project far exceeded what Morgan's investment could support. The theoretical work required to optimize the system was more complex than Tesla had anticipated, and the equipment needed to generate the required power levels was more expensive than his original estimates had suggested. Tesla found himself in the familiar position of having revolutionary ideas that outstripped available resources. Tesla's requests for additional funding met with increasing resistance from Morgan, who had expected to see commercial applications emerging from the Wardenclyffe project by 1903. Instead, Tesla was asking for more money to pursue theoretical research that seemed to be leading away from practical applications rather than toward them. The tension between inventor and investor grew as Tesla struggled to explain why his wireless system required more time and money to reach commercial viability. The conflict with Morgan was complicated by Tesla's growing realization that his wireless technology had implications that went far beyond what he had originally envisioned. During his work at Wardenclyffe, Tesla began to understand that wireless communication and power transmission were part of a larger technological revolution that would transform human civilization in fundamental ways. He started speaking about a world where information and energy would flow freely across the planet, where geographical barriers would become irrelevant, and where human knowledge would be accessible to everyone regardless of location. Tesla's vision of a wireless world was decades ahead of its time, anticipating developments that would not become reality until the internet age of the late 20th century. But his ability to see so far into the future also made it difficult for him to focus on the immediate practical applications that his investors demanded. Tesla was designing systems for a world that did not yet exist, using concepts that would not be fully understood until long after his death. The gap between Tesla's visionary thinking and commercial reality became unbridgeable when Guglielmo Marconi successfully transmitted the first wireless signal across the Atlantic Ocean in December 1901. Marconi's achievement, while technically less sophisticated than Tesla's wireless system, demonstrated practical wireless communication in a way that captured public attention and investor interest. Suddenly, Tesla found himself competing with a technology that was simpler, cheaper, and more immediately useful than his own complex wireless power system. Tesla's response to Marconi's success revealed both his scientific integrity and his commercial naivety. Rather than simplifying his own wireless system to compete directly with Marconi's radio technology, Tesla insisted that his approach was fundamentally superior and would eventually supersede all competing systems. He was probably correct from a technical standpoint, but his refusal to compromise his vision for commercial advantage would prove costly. J.P. Morgan's patience with Tesla's project finally expired in 1906 when the inventor requested additional funding for modifications to Wardenclyffe that would enable wireless power transmission on a global scale. Morgan had invested in wireless communication technology and had no interest in funding what he saw as Tesla's increasingly grandiose and impractical schemes. The financier withdrew his support, leaving Tesla without the resources needed to complete his wireless project. The collapse of the Wardenclyffe project marked the beginning of Tesla's decline from the heights of scientific celebrity to increasing isolation and financial difficulty. The man who had revolutionized electrical power and pioneered wireless technology found himself unable to secure funding for the research that consumed his thoughts. Tesla's reputation as a visionary had become a liability, as potential investors viewed his projects as too ambitious and too far removed from immediate commercial applications. Tesla spent the remaining years of the 1900s struggling to maintain his research activities while searching for new sources of funding and support. He continued to work on wireless technology, but without the resources of Wardenclyffe, his experiments were limited to theoretical studies and small-scale laboratory work. The grand vision of a wireless world would have to wait for future generations to implement, using principles that Tesla had discovered but could not bring to commercial fruition. The failure of Wardenclyffe was more than a financial setback for Tesla. It was a fundamental challenge to his identity as an inventor and visionary. For the first time in his career, Tesla had been unable to translate his scientific insights into practical applications that others could understand and support. The experience forced him to confront the limitations of pure genius in a world that demanded not just innovation, but also compromise, patience, and political skill. As the first decade of the 20th century drew to a close, Tesla found himself at a crossroads that would determine the direction of his remaining years. He could continue pursuing his most ambitious visions, accepting the isolation and financial hardship that such pursuit entailed, or he could scale back his ambitions to focus on more practical applications that might restore his commercial viability. The choice he made would reveal much about his character and set the tone for the final chapters of his extraordinary life. Tesla chose the path that defined his entire existence. He would pursue his visions regardless of the cost. The decade of the 1910s would see him become increasingly isolated from the mainstream scientific community, yet paradoxically more prolific in his theoretical work than ever before. While other inventors focused on incremental improvements to existing technologies, Tesla's mind raced ahead to concepts that would not be understood for generations. The financial pressures following the Wardenclyffe collapse forced Tesla to move from his comfortable laboratory facilities to smaller, more modest quarters. He established a new workshop in the Metropolitan Tower in Manhattan, a space that was cramped compared to his previous installations, but sufficient for the theoretical work that now dominated his research. The physical limitations of his new environment actually helped focus his attention on the mental experiments that had always been his greatest strength. During this period, Tesla began developing what he called his dynamic theory of gravity, a comprehensive attempt to explain gravitational phenomena through electromagnetic principles. The theory represented Tesla's most ambitious scientific undertaking, seeking to unify the fundamental forces of nature in ways that conventional physics had not yet attempted. Tesla believed that gravity was not an inherent property of matter, but rather a manifestation of electromagnetic fields operating at frequencies beyond current detection capabilities. The gravitational theory emerged from Tesla's conviction that the universe operated according to electrical principles at all scales, from the smallest atomic interactions to the largest cosmic phenomena. He proposed that space itself was filled with a medium that could transmit electromagnetic waves, and that what appeared to be gravitational attraction was actually the result of electromagnetic pressure, differentials created by the interaction of matter with this universal medium. Tesla's gravitational work was conducted entirely through mathematical analysis and thought experiments, as he lacked the resources to build apparatus capable of testing his theories. He filled hundreds of pages with calculations exploring the implications of his electromagnetic model of gravity, working out predictions for phenomena that would not be observable with early 20th century technology. The work represented pure theoretical physics of the highest order, but it also isolated Tesla further from experimental scientists who demanded empirical verification of theoretical claims. The scientific community's response to Tesla's gravitational theory ranged from polite skepticism to outright dismissal. Einstein's recently published theory of special relativity was gaining acceptance among physicists, offering a different approach to understanding space, time, and gravity that seemed more mathematically rigorous than Tesla's electromagnetic model. Tesla found himself defending ideas that were increasingly seen as outdated, even though his own work had anticipated some developments that would not be recognized until decades later. Tesla's isolation from mainstream science was deepened by his growing reputation for making spectacular claims that could not be verified. He announced the development of a death ray capable of destroying aircraft at distances of hundreds of miles, a claim that attracted sensational press coverage, but also reinforced perceptions that Tesla had become more of a showman than a serious scientist. The death ray, which Tesla called his teleforce system, was based on legitimate principles of particle beam acceleration, but Tesla's descriptions of its capabilities went far beyond what his theoretical work could actually support. The Teleforce project represented Tesla's attempt to apply his understanding of high-frequency electrical phenomena to military applications. He proposed using powerful electrical fields to accelerate charged particles to enormous velocities, creating beams that could disable enemy aircraft or missiles. The concept was scientifically sound, in principle, anticipating particle accelerator technology that would not be developed until after World War II, but Tesla's claims about the practical capabilities of such weapons were exaggerated beyond credibility. Tesla's tendency towards sensational announcements was partly a product of his financial desperation. Unable to secure funding through conventional scientific channels, he increasingly relied on publicity to attract the attention of potential investors. Press conferences and newspaper interviews became Tesla's primary means of communicating his ideas to the world, but the journalistic format encouraged dramatic claims rather than careful scientific exposition. The media's portrayal of Tesla during this period created an image of the mad scientist that would persist long after his death. Newspaper articles described him as a mysterious figure, working alone on incomprehensible inventions, surrounded by electrical apparatus that sparked and crackled with dangerous energy. While these descriptions captured some aspects of Tesla's personality and working methods, they also distorted public understanding of his actual scientific contributions. Tesla's personal life during these years reflected his professional isolation. He had never married, explaining to friends that his devotion to scientific research left no room for domestic relationships. He lived alone in a series of New York hotels, maintaining a rigid daily routine that included long walks through the city, meals at the same restaurants, and solitary evenings spent reading and calculating. His only close relationships were with the pigeons he fed daily in city parks, creatures that seemed to provide him with the companionship he could not find among humans. The eccentricities that had always marked Tesla's behavior became more pronounced as he aged. His obsessive-compulsive tendencies intensified, requiring him to count his steps, calculate the cubic volume of food before eating, and arrange objects in patterns that satisfied his need for mathematical precision. Hotel staff learned to accommodate his peculiar requests, understanding that the famous inventor's oddities were harmless if carefully managed. Tesla's financial situation deteriorated steadily throughout the 1910s and 1920s. The royalty payments from his alternating current patents had ended with his voluntary cancellation of the Westinghouse contract, and his more recent inventions had failed to generate significant income. He was forced to move frequently as he fell behind on hotel bills, relying on the charity of friends and admirers to maintain even basic living standards. Despite his financial hardships, Tesla continued to work with undiminished intensity on theoretical problems that fascinated him. He developed detailed plans for wireless power transmission systems that would make his Wardenclyffe project seem modest by comparison. He envisioned networks of transmission towers that could provide free electrical energy to the entire world, eliminating the need for power lines, coal-fired generators, and the industrial infrastructure that supported conventional electrical systems. Tesla's wireless power concepts were based on his understanding of the Earth as a resonant electrical system that could be excited to carry energy efficiently across vast distances. He calculated the precise frequencies needed to establish standing waves in the planet's electrical field, designed transmitters that could generate the required power levels, and worked out the engineering details of receivers that could extract electrical energy from the Earth's field at any location. The theoretical foundation for Tesla's global power system was sound, but the scale of the project exceeded anything that could be attempted with available technology and resources. Tesla was designing systems that required power levels comparable to those generated by entire cities, transmitted at frequencies that would interfere with all existing electrical equipment. The practical obstacles were insurmountable, but Tesla continued to refine his designs as if implementation were merely a matter of time and funding. Tesla's work on wireless power transmission led him to broader theories about the electrical nature of biological processes. He proposed that living organisms were essentially electrical systems that could be influenced and controlled through the application of appropriate electromagnetic fields. This concept, which he called bioelectrical engineering, anticipated developments in bioelectronics and neurostimulation that would not emerge until the late 20th century. The biological applications of electromagnetic fields became one of Tesla's most controversial areas of research. He claimed to have developed techniques for using electrical currents to enhance human health, increase mental capacity, and even extend lifespan. These assertions, while based on legitimate observations about the electrical properties of living tissue, went far beyond what Tesla's experimental evidence could support. Tesla's health claims attracted attention from both medical researchers and charlatans seeking to exploit public interest in electrical healing devices. Legitimate scientists were intrigued by Tesla's observations about the effects of high-frequency currents on biological tissue, but they were skeptical of his more extravagant therapeutic claims. Meanwhile, unscrupulous entrepreneurs began marketing Tesla coils and other electrical devices as miracle cures for various ailments, trading on Tesla's reputation while ignoring his actual research. The commercialization of Tesla's name for dubious medical devices distressed the inventor, who saw his scientific work being misrepresented for fraudulent purposes. He attempted to distance himself from the medical device industry, but his financial desperation sometimes forced him to accept consulting fees from companies whose practices he privately deplored. These compromises added to Tesla's sense of isolation and contributed to his growing bitterness about the commercialization of scientific research. As the 1920s progressed, Tesla found himself increasingly forgotten by a scientific community that had moved on to new theoretical frameworks and experimental techniques. The rise of quantum mechanics and relativity theory had shifted physics toward mathematical abstractions that seemed to have little connection to Tesla's electromagnetic worldview. Young physicists were more interested in atomic structure and nuclear phenomena than in the classical field, theories that had dominated Tesla's work. Tesla's response to these developments was to retreat further into his own theoretical world, developing increasingly complex mathematical models that attempted to explain quantum phenomena through electromagnetic principles. He refused to accept the probabilistic interpretation of quantum mechanics, insisting that the apparent randomness of atomic behavior must reflect hidden electromagnetic variables that could be discovered through sufficiently detailed analysis. Tesla's rejection of quantum uncertainty aligned him with Einstein, who famously declared that God does not play dice with the universe. But while Einstein's objections to quantum mechanics were based on sophisticated mathematical arguments, Tesla's criticisms reflected his deep-seated belief that all physical phenomena must have deterministic electromagnetic explanations. This philosophical position put him increasingly at odds with the direction of modern physics. The Great Depression of the 1930s brought Tesla's financial difficulties to a crisis point. His modest income from consulting work and patent licensing disappeared as companies struggled to survive the economic collapse. He was forced to rely entirely on the charity of friends and the occasional generosity of hotel managers who allowed him to accumulate unpaid bills in exchange for the prestige of housing the famous inventor. Tesla's 80th birthday in 1936 brought a brief revival of public attention to his contributions to electrical technology. Newspapers published retrospective articles about his role in developing alternating current and wireless communication, and scientific organizations honored him for his pioneering work. The recognition was gratifying but also bittersweet, as it emphasized how far Tesla had drifted from his former prominence in the scientific community. The birthday tributes also highlighted the gap between Tesla's actual achievements and the mythical status he had acquired in popular culture. Press accounts described him as the inventor of radio, the creator of modern electrical power systems, and the prophet of a wireless future, but they also perpetuated misconceptions about his work and exaggerated his role in developments that had involved many contributors. Tesla used the occasion of his 80th birthday to make one final attempt to interest the scientific community in his theoretical work. He announced the completion of his dynamic theory of gravity and offered to present his findings to any qualified physicists who might be interested. The response was polite but unenthusiastic, as the physics establishment had little interest in revisiting electromagnetic theories of gravitation that seemed to conflict with both relativity and quantum mechanics. The final years of Tesla's life were marked by increasing physical frailty and growing detachment from the world around him. He continued to work on theoretical problems with undiminished mental acuity, but his body was failing after decades of self-imposed stress and neglect. He rarely left his hotel room, except for his daily walks to feed the pigeons, maintaining his connection to the outside world primarily through newspapers and occasional visits from admirers. Tesla's last major public appearance came in 1940 when he granted a final interview to a science reporter who wanted to document the inventor's thoughts about the future of technology. Tesla spoke with remarkable clarity about developments he believed would transform human civilization: global wireless communication networks, artificial intelligence, automated manufacturing, and space exploration. His predictions proved remarkably accurate, anticipating technologies that would not emerge until decades after his death. The interview revealed that Tesla's mental powers remained formidable even as his body deteriorated. He could still perform complex calculations mentally, visualize intricate mechanical devices, and articulate sophisticated theories about electromagnetic phenomena. But he also displayed the increasing isolation and bitterness that had marked his later years, expressing disappointment about humanity's failure to embrace the peaceful applications of his wireless technology. Tesla's final months were spent in room 3327 of the New Yorker Hotel, where he continued working on theoretical problems despite his failing health. Hotel staff reported that he maintained his rigid daily routine until the very end, counting his steps as he paced his room, calculating the dimensions of objects around him, and feeding the pigeons that gathered outside his window. On January 7, 1943, Nikola Tesla died alone in his hotel room at the age of 86. The maid who discovered his body reported that he appeared to have died peacefully in his sleep, his papers scattered around him as if he had been working until his final moments. The man who had illuminated the world with alternating current had slipped quietly into darkness, leaving behind a legacy of revolutionary innovations and unfulfilled visions. The immediate aftermath of Tesla's death sparked a brief renewal of interest in his contributions to electrical technology. Government officials seized his papers, concerned that his theoretical work might contain military secrets that could affect the ongoing World War. Scientists and engineers who had dismissed Tesla as an eccentric during his later years began to recognize the prescience of many of his ideas about wireless communication and electromagnetic phenomena. But perhaps the most fitting tribute to Tesla's genius was the gradual realization, over the decades following his death, that many of his most visionary concepts had been decades ahead of their time, rather than the fantasies of an aging inventor. The wireless world he had envisioned became reality with the development of radio, television, and eventually the internet. His dreams of global communication networks materialized through satellite technology and fiber optic cables. His concepts of remote control and automation evolved into modern robotics and artificial intelligence. Tesla died believing that his greatest contributions lay in the future, in technologies that would transform human civilization in ways his contemporaries could barely imagine. History would prove him correct, though the transformation would take far longer than he had hoped and would follow paths he had not anticipated. The boy who had been born during a thunderstorm and declared a child of light had indeed illuminated the world, though the full brightness of his vision would not be seen until long after the inventor himself had passed into history. Tesla's story is the story of humanity itself, the eternal tension between what we can imagine and what we can achieve. From that thunderstorm in Smiljan to his final moments in New York, he lived as a bridge between two worlds, the one that was and the one that could be. His alternating current powers our cities, his wireless principles connect our devices, his remote control concepts guide our machines. But perhaps his greatest gift was not any single invention, but the audacity to dream beyond the possible. Today, as we stand on the brink of new technological revolutions, Tesla's life reminds us that the future belongs to those willing to see what others cannot, to pursue what others fear, and to persist when others surrender.